Welcome, everyone. Today, we will explore various aspects of applied microbiology, including its importance, applications, and recent advancements. I hope you find the session informative and engaging. Let's get started. Let's dive into the core aspects of food preparation, specifically focusing on determination and the factors that affect heat resistance. Understanding these factors is crucial because they influence how effectively we can eliminate pathogens during processing. One key concept here is thermal death time, which is the minimum amount of time required to kill a specific microorganism at a certain temperature. This helps us design safe processing methods. Now, building on that, we have the thermal process itself. This refers to the controlled application of heat to food to ensure safety and extend shelf life. By understanding the thermal death time, we can determine the appropriate temperature and duration needed for effective sterilization or pasteurization. This entire process is central to ensuring that food products are safe for consumption while maintaining quality. So, in essence, these factors and concepts form the backbone of designing effective food safety protocols. Let's talk about the factors that affect heat resistance in food. First up is water activity, which essentially measures how much free water is available for microbial growth. The higher the water activity, the more susceptible microbes are to heat. Next is pH, or acidity level. Foods with a lower pH, meaning more acidic, tend to enhance heat resistance, so we need to adjust processing accordingly. Then there's fat content. Higher fat levels can actually protect bacteria from heat, making them harder to eliminate. Lastly, the presence of spores is a critical factor. Spores are particularly resistant structures, and their presence can significantly influence how we approach heat processing. Understanding all these factors is crucial because it helps us determine the right heat treatment conditions. This ensures that our food is safe to eat and maintains a good shelf life. Keeping these points in mind allows us to optimize our processes and deliver safe, high-quality products. Water content plays a crucial role in microbial heat susceptibility. When microorganisms have higher water content, they tend to be more vulnerable to heat. This is because the increased water facilitates protein denaturation, which is a key process leading to microbial death. Essentially, the more water present, the easier it is for heat to disrupt their proteins, making sterilization or pasteurization more effective. So, understanding this relationship helps us optimize heat treatments in food safety and sterilization processes. It's a great example of how the physical properties of microbes influence how we can control or eliminate them effectively. Acidic conditions can actually enhance the heat resistance of some microorganisms, making them more resilient when exposed to higher temperatures. This is an important point because it shows how environmental factors can influence microbial survival. On the flip side, alkaline conditions tend to reduce their heat resistance, making microorganisms more vulnerable. Understanding these effects helps us better control microbial growth and ensure safety in various processes. Throughout this presentation, we've emphasized how environmental pH can significantly impact microbial behavior, and this is a key example of that concept in action. Now, let's talk about spore formation. Bacteria that form spores, such as those in the genera Bacillus and Clostridium, are particularly interesting because they exhibit significantly higher heat resistance compared to their vegetative cell counterparts. This means that spores can survive harsher conditions, making them a key concern in sterilization processes. It's also important to recognize that different species, and even different strains within a species, can show varying levels of heat resistance. This variability can influence how we approach food safety and sterilization methods because not all bacteria respond the same way to heat. Understanding these differences helps us appreciate the complexity of microbial behavior and highlights why tailored approaches are often necessary to effectively control microbial contamination. This ties back to the overall theme of our presentation, which is to better understand microbial resilience and how to manage it effectively. Let's take a closer look at the overall food composition. When we talk about this, we're referring to the presence of proteins, fats, and other components within the food. These elements are not just nutritional factors. They actually play a crucial role in how heat penetrates the food during processing. For example, foods with higher fat content might heat differently compared to those with more protein or water. Additionally, the composition can influence microbial heat resistance. Some microorganisms are more resistant depending on the food matrix they're in, which means understanding the food's makeup helps us optimize heat treatment to ensure safety. So, the key takeaway here is that knowing the overall composition isn't just about nutrition. It directly impacts how effectively we can sterilize or cook food to eliminate pathogens. This connects to the broader theme of ensuring food safety through effective heat processing. Now, let's look at the measurements we use to compare how different organisms respond to increased temperatures. First up is the thermal death point, or TDP. This is the lowest temperature at which all microbes in a liquid suspension are killed within 10 minutes. It helps us understand the temperature threshold for microbial destruction. Next is the thermal death time, or TDT. This measures the minimal temperature needed to kill all microorganisms when we keep that temperature constant. Essentially, it tells us how long it takes at a specific temperature to achieve total sterilization. Finally, there's the decimal reduction time, often called D-value. This is particularly useful for heat-resistant bacteria. It indicates the time required at a given temperature to reduce the microbial population by 90%. So, if you start with a certain number of bacteria, after this time, only 10% will remain. It's based on the concepts of logarithmic growth and death, which helps us quantify resistance. Connecting this to our overall theme, these measurements are crucial for designing effective sterilization protocols and understanding microbial resistance in various settings. Let's talk about the thermal death time, or TDT. This is basically the amount of time it takes to kill a specific number of microorganisms at a particular temperature. It's a really important concept when we're looking at sterilization processes, especially in areas like food preservation, cosmetics, and pharmaceuticals. The key idea here is that TDT is determined by keeping the temperature steady and then measuring how long it takes to eliminate a set number of cells. It's not just about how hot it is, but how long you need to maintain that temperature to effectively kill the microorganisms. You can think of TDT as a way to quantify the lethality of heat in sterilization. Interestingly, it's often represented using a logarithmic relationship with temperature, meaning that small changes in temperature can significantly affect the time needed to kill microorganisms. So, understanding TDT helps us optimize sterilization processes, making sure they are efficient and effective, by knowing exactly how long to apply heat at a given temperature to achieve the desired level of microbial kill. This connection to temperature and time really underscores the importance of precise control in sterilization procedures. Let's talk about the importance of TDT, or thermal death time. It really is a key factor in making sure that heat sterilization processes are effective. Without understanding TDT, it would be difficult to guarantee that harmful microorganisms are fully eliminated. Now, moving on to applications. TDT is widely used in food canning. It helps us determine the right heating times needed to kill bacteria and keep food safe for consumption. This is crucial for preventing foodborne illnesses. TDT also plays an essential role in the cosmetics and pharmaceutical industries, where sterilization is absolutely vital to ensure product safety and efficacy. Finally, let's look at the relationship between TDT and temperature. As the temperature increases, the thermal death time actually decreases. This means microorganisms are inactivated faster at higher temperatures. It's a fundamental principle because it explains why heating at higher temperatures can achieve sterilization more quickly, which is important for designing efficient processes. So, understanding TDT and its relationship with temperature helps us optimize sterilization methods across different industries, making sure they're both effective and efficient. Now, let's take a closer look at the thermal death time curve. This curve illustrates the relationship between TDT and temperature. Essentially, it's a plot that shows TDT values on a logarithmic scale against the corresponding temperatures. What this helps us do is visualize how the time needed to kill microorganisms decreases as the temperature increases. This is crucial because it allows us to determine the TDT for different microorganisms at various temperatures, which is vital for designing effective thermal processes. Moving on, I want to highlight the d-value, or decimal reduction time. This is a key concept because it tells us how long it takes at a specific temperature to reduce the microbial population by 90%, or 1 log cycle. Think of it as a measure of how quickly a particular temperature can achieve a significant microbial reduction. Understanding the d-value helps us optimize heat treatments, ensuring safety and quality without overprocessing. Together, the TDT curve and d-value give us a comprehensive understanding of thermal inactivation, which is central to controlling microbial growth in food safety and sterilization processes. Let's talk about thermal processing, a key method we use to preserve food. Essentially, it involves applying heat to food to inactivate harmful microorganisms and enzymes that can cause spoilage. By doing this, we significantly extend the shelf life of food products and improve their safety for consumers. The process works by heating the food to specific temperatures for a set amount of time. The goal here is to eliminate dangerous pathogens and spoilage agents, but it's also important to do this in a way that minimizes any negative effects on the food's quality, like texture or flavor. You'll notice that thermal processing is a foundation for many preservation techniques we rely on, such as canning, pasteurization, and sterilization. These methods are all variations of heating treatments designed to keep food safe and fresh over time. Connecting this to our overall theme, understanding thermal processing helps us appreciate how food safety and quality are maintained through carefully controlled heat treatments. It's a vital part of ensuring the food reaching consumers is both safe and enjoyable. Now let's take a closer look at the mechanism behind thermal processing. When we apply heat, it causes proteins to denature and melts the components of microorganisms and enzymes. This process effectively inactivates them, which is crucial for ensuring food safety and extending shelf life. The main objectives of thermal processing are quite clear. We want to reduce the microbial load, deactivate enzymes that could cause spoilage, and sometimes induce desirable physical or chemical changes in the food to improve texture, flavor, or nutritional value. One common method is canning, where foods are sealed in airtight containers and then heat-treated. This sterilization process ensures that the food remains safe and preserved for years, sometimes even decades, if stored properly. Another key technique is pasteurization, especially for liquids like milk. Typically, milk is heated to around 63 degrees C for about 30 minutes, or it can be heated to higher temperatures for shorter times. This process effectively eliminates harmful bacteria without compromising the milk's quality. Overall, these methods are fundamental in food processing because they balance safety, preservation, and maintaining the desired qualities of the food we consume. Now, let's take a closer look at some of the key thermal processing methods used in food preservation. First, we have retorting. This involves in-package sterilization, where we use high temperatures and pressures to kill bacteria and other microorganisms. It's commonly used for shelf-stable foods, ensuring they remain safe and preserved for long periods without refrigeration. Next, there's blanching. This step is often done before freezing vegetables. Basically, vegetables are briefly immersed in hot water or steam. The main goal here is to inactivate enzymes that can cause quality deterioration over time, like spoilage or loss of texture and flavor. Blanching helps maintain the vegetable's freshness and nutritional value during storage. Finally, we have cooking. This is perhaps the most familiar process, applying heat to make food both safe and enjoyable to eat. Cooking methods like baking, frying, or boiling serve to destroy pathogens and improve flavor, texture, and overall palatability. Connecting this to our overall theme, all these techniques, retorting, blanching, and cooking, are essential tools in food processing. They help us ensure food safety, extend shelf life, and preserve quality. Each method is tailored to different types of food and desired outcomes, but they all share the common goal of making food safe, tasty, and convenient for consumers. Let's take a closer look at the canning process. This is a critical step in preserving food, ensuring it stays safe and tasty for long periods. The process begins with selecting fresh, high-quality produce or ingredients. Next, these are prepared, washed, peeled, cut, or cooked as needed. Once prepared, the items are packed into jars or cans, leaving minimal airspace. Then comes the sealing stage, where airtight lids or seals are applied to prevent any contamination. After sealing, the actual canning occurs through heat processing. This involves heating the jars or cans to a specific temperature for a set period, which destroys bacteria, yeasts, molds, and other microorganisms. This heat treatment is vital because it ensures the product is microbiologically safe and shelf-stable. Finally, the cans or jars are cooled down slowly, which helps maintain the integrity of the seal and the quality of the food inside. Throughout this process, maintaining proper hygiene and precise timing are key to achieving a safe, long-lasting product. This entire process is fundamental to our overall theme of food safety and preservation, highlighting how science and careful technique come together to make our food safe and available year-round. Let's take a closer look at the pasteurization process. This is a crucial step in ensuring the safety and quality of dairy products. Essentially, pasteurization involves heating the milk to a specific temperature for a set period of time, which helps to kill harmful bacteria without compromising the nutritional value or taste. The most common method is the high-temperature short-time process, where milk is heated to about 72 degrees Celsius for 15 seconds. This might sound quick, but it's enough to eliminate pathogens like Salmonella, Listeria, and E. coli. What's important to understand is that pasteurization is not sterilization. It doesn't kill all bacteria, but it significantly reduces the risk of illness. This process is a key part of the overall theme of food safety and quality control, ensuring that consumers receive safe, high-quality dairy products. By implementing pasteurization, producers can prevent foodborne illnesses, extend the shelf life of products, and maintain consumer trust. It's a simple yet powerful step that makes a big difference in our food supply chain. Let's take a closer look at the retorting process. This is a key step in many manufacturing workflows, especially when it comes to improving material properties or preparing materials for subsequent treatments. Essentially, retorting involves heating the material in a controlled environment, often under specific pressures, to induce desired chemical or physical changes. The main goal here is to refine or alter the material's characteristics, such as removing impurities or enhancing durability. It's a crucial process because it directly impacts the quality and performance of the final product. What's interesting is that retorting can vary depending on the material and the specific objectives of the process. For instance, some retorting involves high temperatures over longer periods, while others might require shorter, more intense heat treatments. Connecting this to our overall theme, understanding the retorting process helps us optimize production, improve efficiency, and ensure consistent quality. It's about controlling the environment and conditions to achieve the best possible outcome for our materials. Let's talk about the blanching process. This is a crucial step in food preparation and preservation. Essentially, blanching involves briefly boiling or steaming food, usually vegetables or fruits, to inactivate enzymes that can cause spoilage or deterioration. By doing this, we help preserve the color, texture, and flavor of the product. It's important to note that blanching isn't just about heat. It also prepares the food for freezing or drying by reducing microbial activity. The key here is timing, blanching just enough to achieve these benefits without overcooking, which can lead to loss of nutrients and quality. In the context of our overall theme, blanching acts as a vital pretreatment step that enhances shelf life and maintains food quality. It's a simple yet effective technique that underscores the importance of proper processing methods in food technology. Let's take a closer look at the cooking process. This is a crucial step because it transforms raw ingredients into a finished dish, bringing all the flavors together. Throughout this process, temperature control plays a key role in ensuring the right texture and taste. For example, knowing when to sear or simmer can make a big difference. Timing is equally important. Overcooking can ruin the dish, while undercooking may leave it unsafe or unappetizing. Also, techniques like stirring, flipping, or resting are essential to achieve the desired outcome. Connecting this to the overall theme, mastering the cooking process is about understanding these techniques and applying them thoughtfully to elevate the quality of what we prepare. Thank you so much for your time.